Hey guys, we're back. I wanted to talk a little bit more about magnetism here and some stuff that we need to see. I wanted to remind you, first of all, that whenever you have a charge that's moving, this is what we talked about last time, but here's a charge moving in a magnetic field, it gets a force on it. We used the right-hand rule, we used this formula to find out how much force and the direction of the force. Well, if you had a whole bunch of charges moving in a wire, a current, then you would expect all those charges to experience the same kind of force, and collectively they would put a force on the wire, which could be up and which could even float the wire off of a table or something like that. Here's the formula for this: the magnetic force on a current. The factors that are important, I need to know how much current there is, and the more current there is, then the more force I'll have on the wire. This is the length of the wire that is exposed to the magnetic field. And, clearly if this wire over here is not exposed, then it's not going to have a force on it. But this piece would. B is the magnetic field strength. So we need to know that. The stronger the magnetic field, the stronger the force. This is, again, related to the angle between the current and the magnetic field. And as you change that angle, then that will either, this will maximize sine of 90 would be 1, and so you get a maximum force. If you had 0 degrees, if the wire is running parallel to the magnetic field, in this case that would be into the board, like the magnetic field goes. All right, simple to multiply that, the number, the current, and the length, and the magnetic field. The magnitude. This is a cross product. Force vector I has a direction associated, B has a direction associated. So those actually are the two vectors that you're multiplying. This one is first. So you'd put your fingers in the direction of I on the picture. I is moving to the right. And the second vector, B, is into the board. So you'd curl your fingers into the board and your thumb is forced upwards. And that would be the direction of the force on this thing. So it could float the wire up. If that force were stronger than gravity, then you could have a levitating wire here. Here's a problem like that. Find the current in a wire needed to levitate it. The wire is 50 centimeters long, has a mass of 10 grams, subjected to a constant magnetic field of half a Tesla. So I came over here and drew a force diagram. This is the wire, and gravity, of course, would like to pull that down. So just put mg there, and here's that upward force from the magnetic field. And again, the magnetic field's into the screen with all those x's. I did Newton's second law here. Sum of the forces equals mass times acceleration. You got your two forces. One's up and one's down. One's positive, one's negative. Move the mg over. For the magnetic force there, I put in ILB. It's perpendicular, so I did left off the sine theta, and I solved that for I. You'd have your answer there. I didn't put the numbers in, but you could do that and see what kind of current you would need to make that happen. Okay, this is an interesting case of the same kind of thing. This wire is bent and it follows a path like that. It's a loop. It's a armature, and if you put this loop in a magnetic field, pass a current through it, then you'll actually get rotation here, and we would call this a motor. So this is exactly how an electric motor works. Whether it's AC or DC motor, there's a slight difference, mostly in the way that it connects to the electricity right here. But this one's got a battery, so this would be a DC motor, and the current comes like this. There's a little brush that contacts this, and the current, it goes this way around the loop, and then back. There's your complete circuit right there. So what they've done down here is they've drawn 4 different times where this loop is, and you can use the right-hand rule to see which way the force is going to act on the loop and which way it's going to rotate this thing. Right here in picture A, for example, see how the current's got a dot, it's coming out at you, whereas this one is going in the board. So that would be like over here, this current is coming towards you, and this is going away from you, and so it'd be something like that. If I put my fingers pointing at me, like I see right here, and then I curl them to the right, my thumb has to point up, and so this side gets an upward force. Meanwhile, the other part of the loop, I've got the current going in. In order to curl my fingers to the right to match the magnetic field, I'd have to tip my hand over and my thumb points down. So I get an upward force on this side and a downward force on this side, and that's the direction that this thing would rotate. This force at a distance from right here's the pivot point, moving over to there, force at a distance gives me torque. And so remember that the torque was R cross F, another cross product right there. The R, the distance, is W over 2, where they're taking the entire width of the armature, the loop that turns, and from the center to the edge would be half of that, so W over 2. And then ILB sine theta is the thing there. The angle here is changing at every point. You can see that the angle is marked there and there. And here it's a 90-degree angle, and so different things are. That's as it rotates around. That's going to change. But this is actually that sine theta is probably from the cross product here. So anyway, we're just in here. Think of the second one after it's moved here up to there, right? It was moving up on this side. So now it's up here. That current is coming towards me. I'd point my fingers towards me, curl them to the right. That makes my thumb go upwards. Whereas over here, I'd put my fingers into the board, roll hand over to curl my fingers to the right, and my thumb points down. You go all the way through this thing. This one's kind of interesting right here. With the fingers coming at me, the current coming at me, force. So it's trying to pull this wire upwards. It can't go any farther up. It's rotating around like that. Now you can go get some paper clips and a battery and a couple magnets, and you can make yourself a simple battery, a simple motor, like you see right here. There's a bunch of YouTube videos, make a single loop motor or something. That's kind of a fun thing to do. But you might have done it in middle school or high school or somewhere. But with a super simple motor like that, it's possible for the thing to get hung up right here, and the force trying to pull this side up, not letting it go back down where it needs to. In real life, what you would do is either make this thing heavy enough so that it's got enough momentum to roll past that point, or put a flywheel on it. And there again, that extra weight, once you get this thing moving, it will continue moving as the momentum of it pulls it past that point. Or you would put in multiple loops at different angles, and so that none of those are exactly, it's not just one coil here. You might have another second coil and a third coil and a fourth coil. And together those give you enough to get past that point. But that's a motor. That's a pretty important application of magnetic theory. Check this out. If I have a straight wire and I run a current through it, it generates a magnetic field. There was a guy named Ørsted, something like that. I believe he was Danish physicist, and he was giving a lecture and had a compass and set it down on the table and turned some kind of electricity on, and he noticed that the compass needle moved when he did that. And so it kind of set off this flurry of activity studying electricity and magnetism. Those were previously thought to be two separate fields, and his little accident showed that to be the same thing. So instead of two fields, electricity and magnetism, today we talk about electromagnetic theory, and those have been combined. But right here, what he noticed was that if you pass a current, then you get a magnetic field that surrounds that. There is a right-hand rule that works for this. what you should do is point your thumb in the direction of the current, and then the fingers of your right hand will rotate around. This one I've got my thumb pointed down along that purple wire, and my fingers are pointed to the right. And as I roll my hand around, they continue to make that circle. If I were to put a compass right here, north would point upwards, and here it would point to the right, and here it would point down, and here it would point to the left. And so it makes that circle right there. If I go a little bit farther out, I get a larger concentric circle, and all those magnetic field lines circulate. They go around that wire, and the right-hand rule tells you which way they point. If I want the magnitude, the only thing that really matters here would be the current of the wire. The more current I have, the more magnetic field I have, and how far away am I. So S here represents the distance from the wire to the point where you're interested in finding the magnetic field, and that's really all you have to know. I believe your book uses R. S is a little more generic, so I went with that, but you can put an R there if you want instead of S. I don't care. This constant mu is new, so let me tell you a little bit about that. Down there at the bottom, you see the value of that, and there's two ways to calculate it. One would be 1.257 times 10 to the negative 6. That's measured in Tesla meter per amp. Or you can use the 4 pi times 10 to the negative 7 Tesla meter per amp. It's exactly the same number. If you multiply 4 times pi, then you get the 1257, and you'd move the decimal place over to keep it one significant digit. So that's the difference between the negative 6 and the negative 7. But same unit, same number. Sometimes it's nice to use that second version. You see how there's a pi on the bottom? So if I use the second version, then the pi on the top cancels the pi on the bottom, and I kind of don't have to worry about that part. Okay, but here is an example of that. This one has a loop, so we're letting the current flow here, and then it flows down, and then it flows to the left, and then back up. I've essentially got 4 pieces of wire, and I could find the magnetic field from each one of those and then add those together because they're vectors. This magnetic field that it's generating has a magnitude, it has a direction, and let's do that real quick. Over here, we just wrote down that mu times I, the current, divided by 2 pi s would give me the magnetic field. So if I think about this piece right here, I could use this to find the magnetic field at any point out here. They want at the center of the loop, though. So I'm looking at a spot down here, about right there. Okay. They tell me that the square is 20 centimeters on a side. So if I come halfway down, that would put the center of the wire 10 centimeters or 0.1 meter away from that. So that's what I need to use for S. And so we just put the numbers in. There's our constant 4 pi times 10 to the negative 7 Tesla meter per amp. The current was given to be 10 amps. I've got the 2 pi, and that is that 10 centimeters right there. And see how the pi, there's the pi on the top cancels the pi on the bottom. So that worked out pretty nice. I get 2 times 10 to the negative 5th Tesla for this piece of wire. And I could use my right hand, put my thumb in the direction of the current, point my thumb to the right, and then on this side of the wire, it would be into the board, and I roll my hand up, and on the top side of the picture, it would be coming out of the board at me. So it's going to circle around in a plane perpendicular to the screen that you're looking at right now. All right. When I come down here, all the numbers are the same, so I'm going to get the same value. The right-hand rule says put your thumb in the direction of the arrow. So I've got my thumb pointed down, and my fingers on the left side of the line are pointing into the square, and then they'd be coming back up at me on the right-hand side of the square. So once again, it's pushing magnetic field lines into the board there. And on the bottom, you could do that. Going into the square and coming back up on the outside. And here, same deal. All right. So all we do is multiply by 4 times 10 to the 5th Tesla will be the total magnetic field there at the center of that little loop. Here's a similar problem. This one features 3 wires, I1, I2, and I3, and they're corner of a 1 centimeter square. So you just got those 3 wires. They'd like to know the magnetic field at this first corner right there. So what we can do is find the magnetic field right here based on I1. If I put my thumb in the direction of the current right there, it's into the board. So over at 3 o'clock, if you will, over on the right-hand side of that, B1 is drawn straight down because that's the direction my fingers would be pointing right there. I2, right here, put your thumb into the board at I2, and my fingers are going to make a 45-degree angle at point P. At I3, they'd be going straight to the left right there. So they've drawn those 3 blue arrows to show the directions of the magnetic fields due to current 1, current 2, and current 3. This is a lot like the superposition problems that we did with electric charges and the forces and fields that came from those. We come up here and we say, well, I could calculate B1. It's going to be the same as B3 because the distance here is the same as the distance there. The current's the same, the distance is the same. We just put the numbers in and we get 4 times 10 to the 5th. Right here, B2 is a little bit farther away, so we could use the Pythagorean theorem and get the distance 1 centimeter on a side, so 1.414 centimeters diagonally across there, and that gives us a little bit smaller magnetic field due to 2. So right here, I've just written the 3 vectors. B1 is contributing 4 times 10 to the negative 5th at an angle of 270 degrees straight down. B2 is at that 45 below 180 or 25, and B3 is straight left, which would be 180 degrees. You need to add those 3 vectors to get the total magnetic field at point P. And I haven't done that here. I'm out of room. You could do that pretty easily, though. Just do the little 4-step method, and that would work out fine. Okay. Now, right here, I've got a loop. We could have a single loop of wire. We kind of did that 2 problems ago. Or maybe you have a whole bunch of loops. A single loop of wire, that current would come around like that, and I would get a magnetic field off that, and I could do everything that I've done before, point my thumb in the direction of that current. So as the current goes from here and up the front of this coil right there, I can put my thumb up, and then my fingers on the back side, on the inside of this loop, would point to the right. I'm sorry, to the left. To the left. And so the north pole of that electromagnet would be to the left. And when it comes back down the other side, I'd have to point my thumb down. And again, my fingers on the inside would point to the left, and it comes back around to the outside here. Magnetic fields are always complete circles. It doesn't stop and start the way fields does. It doesn't start at a positive charge and end at a negative charge. Magnetic fields always make complete loops like that. And so as you twist your wrist around, you'll get that complete rotation going around. If I have a bunch of loops, sorry, covered up. I have more than one loop, and on the picture here you can see it making 1, 2, 3, 4, 5, 6, something like 7, 7.5, 6.5 turns, something like that. That's N. That's the number of loops that of wire. This first loop is, the second loop makes that same amount, the third, the fourth, fifth. So if I were doing this, I'd come along and multiply by 6 or 7 or whatever it is, how many ever loops I have. Maybe you have 4,000 loops in there. And the last thing that you have to do here, you see with the mini loops, it's got the mu, it's got the I. We're not really interested in the radius of the loop because it's very uniform. Once you get a solenoid is another name for this coil of loops, and I'm passing the current, generating a magnetic field. That's a classic electromagnet there. But I need to know how tightly those loops are wound. So N over L, the number of loops per length of the coil, tells me how tightly those are wound, and therefore how tightly those magnetic field lines are going to be coming out of that. Okay, your book has this written slightly differently. They have one that says mu little n I, and little n is meant to stand for the number of loops over the length. They refer to it as the number of turns per length or something like that. I like to just put in the number of loops, and then you could measure the length of it. It kind of reminds you a little bit more to do both of those things. But whatever. Here's one of these electromagnetic loop, and I got a whole bunch of loops here, and it goes back. I've got that complete circuit, and that current's going to create a magnetic field and pick up stuff for me and do whatever it needs to do. There's one other way to do the right-hand rule for a solenoid, for a bunch of turns here, and you can see the directions up here on that. If instead of placing my thumb in the direction of the current, my fingers indicating the magnetic field, I can also put my fingers in the direction of the current. So on the front of that coil, they're passing up, and then my thumb would point the north pole of that electromagnet. That's a little bit easier with a whole bunch of loops, but either way will give you the same result. The arrows in the picture like you see there. Okay. How about this? If I have two wires and with currents in them, then there will actually be a force between those two wires. It could be attractive, it could be repulsive. Maybe these two wires that you see here in the picture want to push towards each other or push away from each other. There's some distance apart, R. Here the formula uses S instead of R, the same idea. I can measure the force per length of this thing. There's my mu naught, that constant that we've seen. I1 and I2, clearly the more current this thing has, then the more magnetic field it generates. And the more current this one has, the more magnetic field it generates. And those two magnets will either push on each other and force on the wires. So all of those factors go into it right there. That would be a good one to write down. They'll give you these numbers. You can multiply it out, get the magnitude. Sometimes they ask for the force per length, like that. And sometimes they say the wire is 6 meters long, give me the total force. And so in that case, you multiply this side by L, it would cancel here. And you multiply this side by L, and it would come over, and you just put 6 meters over there. We'll do one of those in just a second. But that's all that's happening. This wire is generating a magnetic field. Now I have a current in a magnetic field, and that creates a force like we talked about on the last slide. So you can see why these push on each other. Here's the way to remember which way they push. If the currents are in opposite directions, the force is repulsive, but if the currents are in the same directions, then the force is attractive. And what I like to remember is that a lamp cord is repulsive. Okay, if I plug in a lamp, the current goes to the lamp in one direction, and then it comes back from the lamp in the opposite direction. Those opposite directions are going to try to push those two conductors apart. All right, a lamp cord is repulsive. Opposite directions, repulsive forces. Here's one of those problems right here. Two 6 meter long straight parallel wires are 10 centimeters apart. One's got 2 amps, the other 5 amps. How much force is between them? Okay, so easy peasy. Right, we got our formula here off the last screen, the force per length. They gave us the length and they want the force. So I'm going to go ahead and multiply both sides by L, leaving the force by itself. There is the L that just came over from the left-hand side. That's my number in 4 pi times 10 to the negative 7. 2 amps, 5 amps, 6 meters. Here's 2 pi. They were a distance of 10 centimeters. We don't like centimeters, so 0.1 meter. And again, you see that the pi on the top and the pi on the bottom cancel each other. I multiply that out, I get 1.2 times 10 to the negative 4 Tesla. Look at all these units. Tesla, meter per amp, amp, meter. And then there's a meter. So I just put all those units there. You see that there's an amp meter on the top and an amp meter on the bottom. So I went ahead and canceled those out, leaving me with Tesla, meter, amp. I remember that a Tesla actually a Newton per amp meter and their amp there. And so the meter amp on top cancels the meter amp on the bottom. I'm left with just newtons, which is good because I was looking for a force. And those would be attractive because they're both in the same direction. If one of them was pointed down, one of the currents over here actually pointed down instead of up, then those would be opposite directions and they would push away from each other. But let's say this is a lamp cord here, right? Yeah, a 6-meter long lamp cord, that's pretty long. 18, 20 feet of lamp cord's pretty long. 10 centimeters apart. Usually our lamp cords are not 10 centimeters apart, but and it would be hard to have lamp cord with 2 amps on one side and 5 on the other. But maybe these aren't lamp cords. Maybe these are separate wires, and so those would be pulled together. But the force is 10 to the negative 4 newtons. Okay, it's a very small force. It's usually not something that we have to worry about. Okay, so that's the second second set of stuff that I wanted you to know about with magnetism. And keep working on the homework list. Any questions that you have, anything that you want to bring up when we get together for recitation, anything that you want to write an email about, you could call, you could come by, whatever works for you. Just that's the main stuff, and when we get together, we'll hammer out the problems with it. Okay. Thank you very much, and have a good day.